Hello again. So we continue our discussions on the heat. Okay, chapter 4, form 4, heat. So question number 28 now, huh? Okay, so before this we have discussed questions number 27, B. Okay, just want to make note here. So at 0 degrees Celsius here, actually what happened is melting. All right. 0 degrees Celsius is the melting point of ice. And then at this point here, we have boiling taking place, whereby liquid will boil and turn into gas. Alright, so that's why here I'm using Q equal to MLF, and then here I'm using Q equal to MLV, because at these 2 points there is no change in the temperature, because we have a change in the state of matter. So let's move on to the next question, question 28. Okay, now you are given a graph of temperature against time. So the diagram above shows the temperature time graph for a substance S of mass 2 kg being heated using a 500 watt electric heater. Okay, so from the questions, I know that my mass, okay, here is my mass 2 kg, and I'm using electric heater, okay, whereby the power is to 500 watt. Okay, before we proceed to the question, let's analyze this graph first. So I have two horizontal line here. So here I must have solid, okay, so here must be solid, and then here I have melting melting taking place. Okay, so here we have melting taking place, and then after it melts, so here I have liquid, and then liquid, and then here must be gas, right? So here is gas. So what is happening at this point DE here? So here is, it must be boiling. So the temperature 70 degrees Celsius, this is my melting point. Okay, takat lebur. And here must be my boiling point. So at melting and also boiling process here, we don't have any change in the temperature. Okay, because we have a change in the state of matter. For example, melting solid will become liquid. So at this point here, we have solid and liquid. Okay. At this point DE here, we have liquid and gas. Okay. So if I am to calculate my heat, so from A to B, okay, so I will use a different color of ink for that. Okay. So from A to B, I'm going to use Q equals MC theta. And at this point here, we are going to use ML of fusion. Okay. Here we have temperature increase from 70 to 90. So again, here we are going to use MC theta. And then here no change in the temperature, so this one must be specific latent heat, in this case liquid to gas, so this must be vaporization. Okay, can you follow? Try to understand it first. All right, let's move forward. Okay, by using kinetic theory, explain why the temperature of substance S in AB is increasing. Okay, the temperature AB, okay, AB, the temperature increased from 30 to 70. So why the temperature increases? Well, the heat absorbed there is used for what? The heat absorbed, okay, is used to increase the kinetic energy. That's why the temperature increases, because the kinetic energy increases. Okay, the kinetic energy of the molecules. Huh? And then next one, by using kinetic theory, explain why the temperature of substance S is constant in BC even though heat is still being supplied to it. So if we go to BC, okay, BC, the temperature remain at 70 degrees Celsius, okay, from 5th to the 15th minute the temperature remains constant. Why the temperature remains constant even though the substance, the material here is still being heated? Okay, so we have talked about this. So the heat absorbed is used for what? Okay, so here the heat absorbed is used to, yes, to break the bond. Okay, to break the bonds between the molecules. So the heat supply here is not to increase the kinetic energy of the molecules, but to break the bonds. So whenever you are breaking the bond, so there must be a change in matter. Okay, a change in the state of matter taking place. Alright, so we go to C, calculate the specific heat capacity of the substance as in solid state. Okay, in solid state. So we are talking about point A, B in the graph. Okay, so Q equals mc theta, right? But who supply the heat? Okay, heat is being supplied by electricity. So that will be PT equals mc theta. So the power 500 watt and the time, okay, the time for AB, if I go to the graph, the time is 5 minutes. Okay, the time here is 5 minutes from A to B. Okay, but again, we don't work with minute, we work with second. So 5 minutes, you convert it to second, that will be 300 seconds. Okay, so the time is 5 minutes, and this is equivalent to 5 times 60, that would be 300 seconds. Okay, so the mass of the substance just now, it was 2 kilogram, right? And we want to find what is the value of our specific heat capacity and what is my theta. Theta is the increment in the temperature. So my temperature increased from 30 to 70. So the increment in the temperature would be 40. 70 minus 30. So the difference in the temperature here is 40 degree Celsius. Okay, so I'm going to substitute the value of theta equals 40 here. Alright, so now we can calculate our C. So our C would be 1875 joule per kilogram per degree Celsius. Okay. Now, let's move to the next one here. Calculate the specific latent heat of vaporizations of substance S. Okay, so here we are talking about specific latent heat of vaporization. So it's Q equal L V. Okay, specific latent heat, so L. Vaporization, so that will be a V here. Okay, but again, who supply the heat? Electricity, that will be PT equals MLV. Okay, I do know that my power is 500 watt. And what about my time? So if I go to my graph, uh, which point are we talking about? Okay, it's MLV, right? So we are talking about point D to E. So what is the temperature? Sorry, what is the time taken? From 20 to 35. So the time taken is 15 minutes. Okay, so we go down. So the time is 15 minutes, but we don't work in minute, we work in second. So we multiply it by 60. So this will give you 900 seconds. Okay, so we substitute t equal 900 into our equation here. Here is 900, okay, equals m. Okay, our mass just now is 2 kilogram. And then we are to find what is our specific latent heat of vaporization. So I believe now we can calculate our LV. That would be 2.25 times 10 to the power of 5 joule per kilogram. Okay, here is joule, right? So joule, I bring my mass to the other side, then joule per kilogram. That is the unit for my specific latent heat of vaporization. Alright, try to understand how we have worked the problem out. Okay, let's move to question 29. Okay, now you are given a method used to determine the latent heat of fusions of ice. So we have diagram A, diagram B, diagram A. I have it being connected to a power supply, and here I have my heater definitely. Here it's not being connected to a power supply. Okay, so what is the function of this diagram B here? What is this diagram for, or what is this setup for? This is what we call, I believe in your biology class you have done this. Okay, so this is what we call as the control set. Okay, so why do I need this control set? Because I want to know, okay, if I don't have any power supply, if the heater is not heating the ice, what effect does the surrounding have, okay, on the amount of ice, or amount of ice being melted, okay, by the surrounding heat. That is what we want to know, okay, from this control set. It's due to the surrounding temperature. Okay, how much of this liquid will be collected due to the surrounding temperature? Okay, so let's answer the question. What is the meaning of latent heat of fusions of ice? So we write it is the amount of heat needed. Okay, so amount of heat needed to change 1 kilogram of ice to water, because we are talking about fusion. So fusion, it must be solid to liquid, liquid to solid. Okay, so here we are talking about the ice, so that's why I have 1 kilogram of ice, okay, to water without any change in the temperature. Okay, so that is the meaning of latent heat of fusions of ice. Now, what is the purpose of a control set as in diagram B? So I have mentioned this earlier. So it is to determine the mass of ice that has melted due to the surrounding temperature. Okay, and then next one, why the immersion heater must be totally immersed into the ice? Well, common sense. Okay, so that the mass of ice that has melted due to the heat from the heater is more accurate. Or we can also say so that all of the heat all of the heat supply is used to melt the ice. Okay, we don't want any heat to be wasted. Okay, D. An immersion heater with 50 watt of power used to supply heat to the ice in 10 minutes. Total melting ice is 85 grams. Calculate the value of specific latent heat of fusion. So, supply by electricity. So, PT. Received by the ice. So, MC theta. Correct? But here, okay, we are talking about melting of ice. Okay, so melting of ice is not about, we don't use MC theta because here we are dealing with melting. So melting, the temperature remain constant. So we are not going to use this MC theta, but we are going to use MLF. Okay, so I'm using a specific latent heat of fusion here because we are talking about a change in the state of matter from solid to liquid or vice versa. All right, so my power is 50. Okay, and then my time is 10 minutes. Remember, we don't work with minute, we work with second. So we convert this minute into second. That will give you 600 seconds. Okay, so now mass is 85 grams and we don't work with gram as well, so we work with kilogram. So convert this into kilogram. You should be able to get 0.085. Okay, just divide this by 1000. You should be able to get 0.085 kilogram, and then multiply by the specific latent heat of fusion. Okay, so now you can calculate your specific latent heat of fusion. And this one you should be able to get the answer 3.53 times 10 to the power of 5 joule per kilogram. Okay, now E. Why the value of specific latent heat of fusion of ice in the experiment is greater. Okay, why it is greater than the actual value? Well, in the real life, nothing is perfect, right? So what happened? Because some heat has lost to the surrounding. This is the reason why we are not able to get a very accurate specific latent heat of fusion. All right. So that's all about specific latent heat of fusions and vaporization. So next we move on to gas law. All right. So in Form 4, we have learned three gas law, namely Boyle's law, Charles' law, and pressure law. And we can combine these three laws into one, the so-called the universal gas law. Alright, so let's go one by one. Boyle's law. What does Boyle's law say? Okay, so Boyle's law states that for a fixed mass of gas, this all the same for a fixed mass of gas. Okay, so for Boyle's law it simply says that pressure, okay, pressure is inversely proportional to volume. Okay, I add some more at the back here, at constant temperature. Okay, so that is Boyle's law. Okay, now what does Charles' law say? So Charles' law says that for a fixed mass of gas, okay, Charles will talk about volume. Okay, it says that volume is directly proportional to the absolute temperature. Okay, this is what Charles' law say. But here, what is constant? Okay, here at constant pressure. Okay, that is what mentioned in Charles' law. Now, pressure law, okay, says that for a fixed mass of gas, okay, a fixed mass of gas, just like before, just like Boyle's law and Charles' law. So it says that pressure, okay, is directly proportional to the absolute temperature. And what is kept constant here other than the mass of the gas? Okay, volume, at constant volume. Alright, so for Boyle's law, it's pressure inversely proportional to volume, okay, constant temperature. Charles' law, volume directly proportional to the temperature at constant pressure. And for pressure law, okay, pressure is directly proportional to temperature at constant volume. So as you can see, all the three laws here, it talk about pressure, it talk about volume, it talk about temperature. All right, so that's why we can combine this and we can form our universal gas law, which is P1 V1 over T1 equals P2 V2 over T2. Okay, you will see me solving problem just by using this universal gas law. But at the same time, you must be also well versed. Okay, what is Boyle's law? What is Charles' law? What is pressure law? All right, so if I go back to my Boyle's law, from this, from what is being said by the law itself, it says pressure is inversely proportional to volume. So here I can write P, pressure inversely proportional to volume. So if I am to sketch a graph of P against V, this graph will be like something like this. All right, it goes down, decreasing. If I am to plot P against 1 over V, so this is going to be a straight line from the origin. Alright, because for this statement here, we can read it two ways. One is pressure is inversely proportional to volume. or you can also say that pressure is directly proportional to 1 over volume. Okay, Charles' law, volume is directly proportional to the absolute temperature. So I must pinpoint here, we are talking about absolute temperature. Here also absolute temperature. So what is absolute temperature? The temperature in Kelvin. Okay, that is our absolute temperature. So if you recall in year form 4, I did mention that only in gas law that the temperature, okay, you must use Kelvin. Okay, you cannot use degrees Celsius. You must use Kelvin to solve problem involving gas law. All right, let's continue our discussions. So here it says that volume is directly proportional to the absolute temperature. So I can write volume is directly proportional to temperature. All right. So if I have V against temperature, I can see here this thing in Kelvin. So it will start from 0, 0, sorry, and it will go straight up. Okay, it's directly proportional. But if my temperature here is degree Celsius, okay, so it is still a straight line, but it doesn't start from 0. Okay, in fact, it will intersect the x-axis here at negative 273 degree Celsius. Okay, so meaning to say that 0 Kelvin is equivalent to negative 273 degree Celsius. Alright, that's why if you are to convert degree to Celsius, you have to add 273. For example, uh, 0 degrees Celsius, okay, is equivalent to 0 degrees Celsius plus 273. Okay, that will be 273 Kelvin. Okay, if I have 100 degrees Celsius, so that will be equivalent to 100 plus 273. So in Kelvin, that would be 373 Kelvin. Alright, follow. Okay, now pressure law. Pressure law, just like volume, it is directly proportional. Okay, directly proportional to the temperature. Remember, the temperature is absolute temperature, so it must be in Kelvin. So if you are to plot P against temperature in Kelvin, just a sketch, not a plot. All right, so it starts from 0, 0, it goes up straight line. Okay, directly proportional. But if your temperature is in degrees Celsius, you will have something like this also, right? Whereby here it intersects the x-axis here at negative 273 degrees Celsius. All right. Okay. So I hope you can follow the discussion. Okay, we move on. The temperature in gas law must be in Kelvin, and then the value of negative 273 degrees Celsius is equivalent to 0 Kelvin. Okay, it's 0 Kelvin, negative 273. So this temperature, okay, this 0 Kelvin is also known as the absolute zero. Okay. That would be the lowest temperature achievable by gas in Kelvin, right? Okay, let's move to the next question. We try to answer these questions. We have diagram A, okay, 18 centimeter of A column. Up here I have mercury, okay, 4 cm of mercury. And then if we invert this, okay, it will become like this. We want to find out what is our L, okay, and then we are also given that the atmospheric pressure is 76 centimeter mercury. All right, so I am to draw because I want to know, okay, I want to know what is the pressure of the air. Okay, so I will draw a line here. Okay, and then I will draw a line here, down here. All right, so what is the pressure here? Okay, the pressure here would be P equals to the pressure exerted by the mercury. That will be 4 centimeter mercury plus the pressure exerted by atmosphere. That will be 76. So here is 76. So the pressure there is 80 centimeter mercury. Okay, so let's say here is P1. What about the pressure here? Okay, I know that from bottom here, I have P atmospheric pressing it up. At the same time, I have air and also the mercury is pushing it down. And they must be in equilibrium. So here I can write P, uh, P atmospheric pressure. Okay, P atm must equal to my P of this mercury. Okay, P mercury plus P of the air. Okay, they must be the same, otherwise this mercury will be going up or going down. Okay, so P atm is 76 equals 4. Okay, plus P of the air. So now I call this as P2. So my P2 is 72 centimeter mercury. Okay, so far are you with me? Alright, so now I'm going to use my universal gas law. Okay, P1 V1 over T1 equals P2 V2 over T2. So in these questions, I don't have any temperature. So I will just cancel this temperature out, assuming that they are equal. So P1 is 80. And then the volume is 18 times the area of the tube, right? So since they have the same area, so maybe I just write here 18 multiplied by the area is A to get the volume. Okay, let's assume let A equal to the base area or the cross-sectional area. All right. Okay, equals to P2. P2 is 72. Okay, and L is what we want to find out. Multiply by the base A. Okay, so I can cancel my A here because they must be the same. Right, so can you calculate your L now? Yes, so your L is 20 centimeter. Okay, so that's how you solve the problem. Alright, so try to understand how we work the question out. So I meet you again in the sec.